now comes a what we would consider a very important example, which we have already studied in the context of the discrete time Fourier transform. So, here is a exponential sequence, but it is of finite length sequence. It is like a moving average filter, except that it is exponentially weighted. Okay. So, x of n is equal to a power n in the region n greater than or equal to 0, less than or equal to n minus 1. Okay. And equal to 0 otherwise. So, you can see that it is a finite length sequence which is exponential in the region that it is specified. Okay, let us write down x of z. X of z is equal to summation n equal to 0 through n minus 1 a power n z power minus n. So, it is a finite length geometric series. So, what we get here is 1 minus a z inverse raised to the power n divided by 1 minus a z inverse. Okay, just apply the geometric series for a finite length sequence. Okay. Now, does the z transform always exist? Yes, the answer is yes, because as long as A is well defined, this sequence will converge, right. So, just to confirm that our understanding is correct, we want mod x of z less than infinity, right, that we want it to be finite. So, which means that this will be less than or equal to summation n equal to 0 through n minus 1 modulus of a z inverse raised to the power n less than infinity. Okay. And so, as long as a z inverse is finite, then that basically means that mod a less than infinity and z not equal to 0. Right. If z equal to 0, then it will explode, and z not equal to 0. So, under those conditions, you will we can safely assume that we are looking at a ROC, a z transform that will converge. Okay, so the ROC for this x of z, for this, so this we can say is the entire z plane, because it is a causal sequence, it has got negative powers of z. So, z equal to 0 will be a pole. So, we will say that except z is equal to 0, you have to exclude z equal to 0, everywhere else it is valid. Okay. Now, I would like to understand the pole zeros and the region of convergence and all of that in a little bit careful manner. Okay. X of z is, if you write down this expression, 1 minus a z inverse raised to the power n, 1 minus a z inverse, if you simplify it, you will get 1 over z power n minus 1, z power n minus a power n divided by z minus a. Just simplifying this expression. But I now have a problem. What is the problem? Look at this term. This is a pole at z equal to a. So, which means that I can only take z greater than a or z less than a. I cannot, this statement that the entire z plane is the ROC, there is a discrepancy between the, we made an argument saying it's a finite length sequence, A is bounded, so therefore, we have the entire z plane. So, is there a inconsistency in terms of our specification? And clearly, if there is a pole at z equal to a, the other statement is wrong, and therefore we must look at. So what we are going to do is take a closer look at the poles and zeros of x of z. Okay. So what are the poles and zeros? Let's take the zeros first. For zeros, z power n minus a power n equal to 0, same as saying z power n is equal to a power n. Okay. Remember the complex roots of unity. So z is equal to a, not just equal to a, you have to also take the complex roots of unity, e power j 2 pi by n times k, because if you take 2 pi by uppercase n, if you now take z power n, a e power j 2 pi by n raised to the power k raised to the power n, you will get a power n. So the general solution is of this type, where k equal to 0, 1 all the way raised to n minus 1. Okay. So let's first sketch the zeros. The zeros are located on a circle with radius equal to a. They start at the origin, k equal to 0, and just for ease of plotting, let us take n equal to 8. So there will be 8 zeros uniformly spaced at 45-degree angle. Okay, 1, 2, 3, 4, 5, 6, 7, 8 zeros are on the unit circle. Now what about the poles? Okay, look at the expression for that. There are n minus 1 poles at z equal to 0. Okay, how do you denote that? You put double x or triple x and then say that in this case n minus 1 is equal to 7, any number of 7 poles. Okay, there are a total of 7 poles at the origin, and there is a pole at z equal to a. That is the key. Okay, there is a pole sitting here. But notice that a pole and a 0 are occurring at the same location. This is called a pole-0 cancellation. Okay, which means that the effect of the pole is actually cancelled by the 0. So when they cancel each other, then what you are left with is 7 zeros on the unit circle except at the origin, that is except at the z equal to a equal to 1, and there are 7 poles which are at z equal to 0. Okay. So now given that all the poles which are not cancelled, which are left in the transfer function, are all at origin, what is the ROC? ROC is the entire, so because of the pole 0 cancellation, ROC is the entire z plane excluding z equal to 0, which is correct because that is what we came up with as the ROC for a finite length sequence. Okay. So sometimes you must be careful to look at the location of pole, because the ROC will, in order to determine the ROC, you would have to first look at the pole locations. And if you looked at the expression for x of z, you may assume there is a pole at z equal to a, and therefore declare that the ROC has to be either greater than mod z greater than a or mod z less than a. However, if there is a pole 0 cancellation, it can change the ROC, and therefore you must be careful with that expression. Now, just like we did for the discrete time Fourier transform, we can apply the property of differentiation to get the Z transform of related sequences. So let us just quickly write that down. A power n u of n has got a Z transform which is given by x of z equal to 1 over 1 minus a z inverse. This is equal to summation n equal to 0 to infinity a power n z power minus n. Okay. Now, if I were to differentiate with respect to z, d by dz of x of z, which is given by d by dz of summation n equal to 0 through infinity a power n z power minus n. If you write down the differentiation, then what you will get is summation n equal to 0 through infinity, take the differentiation inside a power n minus n z power minus n plus 1. Okay. And just one step away, away from the answer, basically you can write down saying that this is equal to summation n equal to 0 through infinity n times a power n z power minus n, there is a minus sign and there is a minus z inverse, there is a minus z inverse. Okay. So, you can easily take it to the other side and obtain a z transform for n times a of n. So, what I would like you to do is to complete the this calculation. So, n times a power n u of n has got a z transform that is given by a times z inverse divided by 1 minus a z inverse whole square. Okay. So, again use this calculation as a reference, find out what is the corresponding thing that you would have to do. So, for example, it will be z times minus z times d by dz x of z will be the expression for n equal to 0 through infinity, n equal to 0 through infinity n times a power n z power minus n. So, this is the differentiation formula that we get for the z transform, and using that you can get the final expression that you can get for this. Okay. So, I hope you are at least having done it for the discrete time Fourier transform, you will feel comfortable to do this for the z transform as well.